Okay, I see there's a pretty long line out there, so I couldn't get through the line myself. Okay, so we're going to spend an hour introducing the Einstein coefficients associated with the Einstein theory of radiation and how that leads us to the absorption coefficient. So imagine you're doing an experiment. You propagate light. You propagate light at a specific wavelength because you know the position of the line you want to study, and you see some attenuation. And you want to relate that attenuation of light back to the density of the species that's absorbing. And that's done with the spectral absorption coefficient. So here's the situation. Imagine a light source. For simplicity, imagine that it's a steady state light source with some intensity. Initial incident intensity, we always write as I superscript 0 or I subscript 0 at frequency nu. So this is a relationship for monochromatic light. Light passes through a sample of gas of length L, and the amount of light that comes out is diminished. And we'll find that the transmitted light divided by the incident light is given by an exponential decay law, where K is the absorption coefficient. So we're going to measure the attenuation. We're going to therefore solve for K. And the question is, what is K? And how does it depend upon the properties of the absorbing species? And there's some other related topics that we'll cover as we go. To do this, we derive what's called the equation of radiative transfer. So we imagine that in this case, that light is entered and that the sum of the absorption, the reflection, the scattering, and the transmission, they must all add to 1. So those are the possibilities. That the light will be transmitted if it's not scattered, reflected, absorbed. Scattering might occur because of particles in the system. Reflection might occur if we have some particles. So we imagine a case in which there's no scattering in particles because whatever relationship we derive for the gas has to hold independent of whether there are particles present. Basically, it's basically conservation of energy over and over again when you do spectroscopy. So we imagine now the case where we've neglected scattering and reflection on the grounds that whatever they are, they can't affect the gas. The properties of the gas must be that it'll either be absorbed or transmitted. Those combined fractions must equal 1. We use a subscript nu to reflect the absorptivity at frequency nu, transmissivity at frequency. What we mean by the absorptivity is the fractional change in I that occurs over that length. So K then is the fractional change in I that occurs per unit length. So K nu dx taken together is the fractional change, di over I. So K is going to be our spectral absorptivity, which is therefore a number per unit length. So K is the fractional change in I per unit length. Therefore, units would be typically centimeters to minus 1. And this is independent, really, now, whether the intensity is in units of watts per square centimeter per unit frequency. Here's watts per square centimeter per unit frequency, different units. It also is true that if you had a pulse of light, you can apply the same relationship. But right now, for simplicity, just think about it as a steady experiment. Now, what do we mean by nu? We really mean the frequency range nu to nu plus d nu over some frequency interval that we're dealing with, because we have some finite interval. Now, if we integrate over frequency, then we could say that the integrated intensity is the integral of I nu d nu. So that would be the total intensity of our source if we think of I as the intensity per unit frequency. Again, that might be watts per square centimeter. Now we go back to this, and we retreat to equations, to courses you hopefully will have had in radiative transfer. We define the spectral emissivity of the medium to be the emission at frequency nu divided by the black body value. So there's no units. It's a fractional. It's a fractional relationship or normalized relationship. So the emissivity is 1. That means it emits like a black body. If the emissivity is 0, it doesn't emit. So there's no units, but this is the black body radiancy. Whether you use black body radiancy or different units for I. As long as you do this the same in the numerator and denominator, you're okay. Emissivity is the propensity for emission. And now you invoke something called Kirchhoff's law, in which emissivity equals absorptivity. Where did that come from? That comes by looking at a situation which is in equilibrium. And you can argue that all microscopic processes have to be balanced. And therefore, you can argue that emissivity has to equal absorptivity, independent of whether you are in equilibrium or not. It's a common strategy in problems in spectroscopy and chemistry is to examine equilibrium, set up the relationships, and then as you retreat away from equilibrium, you can ask which of these relationships still holds. So anyway, the Kirchhoff's law, if you've seen it or not seen it, emissivity equals absorptivity. Therefore, the emission is emissivity times the black body value. The absorption is the absorptivity times the local intensity. And di, which we're interested in here, is the difference between the net emission and the absorption. And if I invoke Kirchhoff's law, then I end up with something I can write in terms of alpha only. So you take emission light, the absorbed light, I could write it now in terms of the absorptivity. And it's the difference then between the black body value and the instantaneous value of intensity. That's the local value that's produced by our laser. This is called the differential form of the equation of radiative transfer that says di is k dx, because k has units per unit length, times this difference quantity. That's called the differential form of the equation of radiative transfer. We haven't said anything yet about the type of spectra these are. We don't care. This is just a general expression. So that's the differential form. We can integrate this over length. We can get what's called the integrated form of the equation of radiative transfer that says the intensity that's emitted, or the exits, is the incident intensity with its attenuation plus this black body contribution of emission. Where L is the path length, which we now assume to be a uniform medium. This quantity, K nu L, is called the optical depth. So there's no, K nu L is dimensionless. So you can see everything depends upon the value of K nu L and the relative values of I nu 0 and IB. So if you either have a laser source or we don't. So now we imagine a collimated beam of light, just to keep things simple. It looks like this. The equation that governs what's going to happen. Some incident light is present, I nu, I0. Some light exits. And everything depends upon only the optical depth and the relative values of these two terms. We consider two cases. Consider emission and we consider absorption. So let's look at the emission experiment. What does the emission experiment mean? Let's imagine we have no external radiation source. If I nu 0 is 0, only thing we're going to see is the emission that comes out. We scrub the first term, and that's the amount of intensity of light coming out. It's the black body value times this quantity. Everything depends upon K nu L. So if you look at it this way, then the emissivity becomes nothing more than the exit intensity divided by the black body value, which is 1 minus e to the minus K nu L. So you see if K nu L is small, that's called optically thin, or K nu L is large, optically thick. If K nu L is large, what do we see? The term goes away, and it's a black body emitter. So if you make K nu L large, that's a black body. If you make K nu L, it's called optically thin. And then you expand this exponential term into 1 minus K nu L, and this emissivity ends up being K nu L. So we have two limits, optically thin and optically thick. But in the case now where we have emission, so we have a hot system, no incident source, this is how we would characterize the emission of this hot gas. Question is, what's K? So you know L, what's K? Depends on the spectroscopy of the gas that you're looking at that has emission at frequency nu. We can integrate this over frequency to look at the entire output of light. We can integrate this over all frequency, and you can solve for the emissivity. And you have to remember hopefully you would have seen this, that the integrated intensity from a black body is sigma t to the fourth. That's called the Stefan-Boltzmann relation, and that's a constant. So the emission from a black body depends upon temperature to the fourth and this constant. That's the emission from a black body. So the emissivity, it still depends upon K. Everything depends upon K. We're going to mostly do absorption, but this is a reminder to us that if you can calculate absorption, you can calculate emission. Now we have to worry about whether we have lines or bands or continuum. There's different types of emission. The key is consider the optical depth. It's either optically thick or optically thin. Now, what about absorption? This is the one we care about. Now we have an incident light source which is hot. That is, its intensity is higher than the black body intensity. Now we scrub the second term. And we cover immediately what's called Beer's law. This is the equation for monochromatic light. That the exit intensity is the incident intensity attenuated by the absorbance. You can use different units for I, but the point is, what is the fractional change? That's given by the absorbance. Okay, this is fine. This is the equation of radiative transfer. We still haven't related it to the molecular properties. What do we care about? It's obviously going to depend upon the number of molecules. It's obviously going to depend upon the density of molecules in the absorbing state. And it's going to depend upon some fundamental property which comes to us from the Einstein theory. This equation would also apply to transmission of a pulse of light at frequency nu, so we could think of this as E nu over E nu 0, as well as intensity of a continuous source, because it's just fractional attenuation of the photons. The question then is, how is K nu related to these fundamental molecular parameters? So remember, we have line positions, line strengths, line shapes. We now know enough about line positions. So we imagine we're parked on one of these lines. We understand the strength of the process. To do this, we introduce the Einstein theory in two steps. First, I introduced what's called the Simplified or Milne Theory. And this introduces some things that you might not have seen before. So imagine a quantum state 1, always represented by energy here, constant line, and energy state 2. So we're going to pick two energy levels which are allowed to have transitions. We recognize that if there's a molecule here, it can have what's called spontaneous emission with a probability A per second of emission. That's the probability of the process for each atom in this state. So these coefficients, A, A21, B12, B21, are the Einstein coefficients. They were introduced by Einstein long ago and well before lasers, so the notation is a little awkward in places. But he says that the fundamental processes we have to worry about are spontaneous emission, absorption, and induced emission. Those are the three elemental processes that are responsible for the spectra. So the energy difference is h nu, Planck's constant, and the frequency. And here we state 1, state 2, and now we can say, what is the total number of molecules per second undergoing this process? Well, the total number in 2, and capital N usually denotes the total number. So the total number undergoing this process per second would be N2 times the probability A21. So that's the number of molecules going from 2 to 1 by spontaneous emission. What does spontaneous emission mean? It means we don't actually know what's going to happen. When you have a microscopic system, there's something called the uncertainty principle that says you can't tell me exactly when this is going to happen. I can talk about a probability or an average, but I can't say exactly. That's the nature of a microscopic system. You can also have absorption of light, and he defines that probability as B12 times what he calls, here it is down here, is the probability per second that a molecule in 1 exposed to radiation of density rho nu, these are awkward units, will absorb a photon, a quantum, and pass to 2. In this system that Einstein introduced, this B coefficient has awkward units, but it's basically the density of photons per unit volume. Of course, the photons move at the speed of light, and we're going to convert this to a laser shortly. But this is the way he did it. So these are the notations that tell us probabilities or numbers per second undergoing these three processes. Now, what do we know? I was saying earlier, we frequently consider equilibrium and then ask what still holds away from equilibrium. Because at equilibrium, all processes are balanced. All microscopic processes are balanced at equilibrium. So here's our problem. Now we do what's called detailed balance. What is the rate of change? So n2 dot means the time derivative of the number in 2 due to this radiative process. Well, it would be the number which are brought in by absorption minus those which are leaving due to the combination of spontaneous emission and induced emission. What do we know about equilibrium? That net number must be 0. Changing at equilibrium, the net. Well, we know something else about equilibrium. We know the Boltzmann relationship. So we know that N2 over N1 over here is the ratio of the degeneracies and e to the minus, so this is e to the minus delta E over KT. So we know two things about this relationship. When you set this equal to 0, you can solve for N2 over N1 and you get this result from here. Now we impose what we know from statistical mechanics. They both must be true at equilibrium. We all know something else. We know the photon density from the Planck distribution that comes to us from if you combine these terms, recognizing we know the answer for rho nu at equilibrium, combine these terms, you can find that rho nu then can be expressed two ways, either in terms of the A and the B's or just the Planck distribution. Therefore, in order for us to have these relationships equal, we find that G1, B12 must equal this. And we know that A is related to B. We also will say that if the probability per second of emitting, that there's an average time, it's called the average radiative lifetime, that's 1 over A is tau. So by going to equilibrium, we found that this must be true always, period. These are relationships between the now introduced Einstein coefficients that come to us. That simplifies our problem. Now I go away from Einstein's awkward units of radiation intensity, and I say, well, let's imagine we have light that's propagating at the speed of light. So now I can relate rho and I, recognizing that the photons move at the speed of light. So now that's fine, but I still don't have the link to K. We're after K. So how do we combine things? We're going to go back to an energy balance. We haven't yet addressed the shape of lines. I don't know what they are yet. So we're going to imagine that here's an individual line, that there's some absorption over some width, delta nu. I don't yet know what the shape of that line is. If there's a transmission dip, that means that I can define K. Remember, K is the fractional change in I per unit length. So here's now a plot of K. So I take the logarithm of the observed transmission and plot the negative logarithm and plot, that's K. So I don't yet know the shape of this line. I know that it's centered at nu 0, and it has some magnitude, and it has some width. Now I use conservation of energy to look at the incident light in a frequency interval that's coming in and then going out. I can say that the absorbed power must be the incident power times the fraction absorbed. I can therefore, I'm talking about some packet of light of frequency interval delta nu. And the transmission is e to the minus k nu. So I remember now I have optically thin, I've got optically thick. I can do this exactly, but let's look at this in the optically thin limit. That means k nu dx is small. So the absorbed light is the incident light times k nu dx. So the fraction absorbed is k nu dx. I get fraction absorbed in these units in the radiation transfer theory, and now I got to combine this with the Milne theory. I got to go to the Einstein theory. So go back to induced emission. I've got induced emission, I've got spontaneous emission, I've got induced absorption. And imagine that I have collimated light, which I'll have for a laser. And in that case, the spontaneous emission, which goes by into 4 pi steradians, is a small number, so it can be set to 0. Again, you examine a limiting case to find the relationships that then hold away from the limiting case. So I can look at the induced emission, and now use lowercase letters for the number per unit volume. Previously used capital letters for the total number. So this is the number of molecules in level 2 at an instant in time. State 2, number per unit volume times the path length dx times the probability of emission in Einstein's system times the energy per photon. So this is basically the number of photons per second times the energy per photon. I do the same thing for the absorption. I now invoke my simplification to relate Einstein's units to mine of intensity. Write it out. So here's the delta. So it's the difference between these two terms. This is the differential. This is the emission followed by the absorption. And by doing this and relating it back to K, remember di over I nu dx is K, I solve for K. So now, finally, kind of quickly really, I have found that the K that we care about, the absorptivity coefficient, is nothing more than constants, 1 over delta nu, the width of the not yet understood line, number density of absorbers, find B12. This is called the induced emission term, usually essentially 1. So what do I see? The absorption per unit length depends on the number of molecules in the absorbing state, number per unit volume, times the propensity for absorption, B12, divided by the width. So I've still got this width floating around, but now for the first time I know the absorption per unit length is proportional to the number of molecules and the Einstein coefficient and some constants. So if you tell me the Einstein coefficient and the number density in level 1, I can give you the absorption coefficient, and we can interpret the attenuation of the light beam. But we got this nasty little delta nu still floating around. So we can anticipate that we have to retain the line shape information. So we're going to introduce next a realistic line shape. See what happens. So a bit of a jump here. And so I'm going to topic 3. So what we know actually is that the absorption, if I plot the absorption absorbance versus wave number for a case like this, water vapor of mole fraction of 0.1, path length of 5 centimeters, probably room temperature, taken from high tran at different pressures, here's the absorbance. It has shape. As you go up in pressure, it has shape. So we realize that we have to pay attention to this shape to get the actual absorbance at a specific frequency. So we're back to this relationship again. We have this integrated form. We have to decide typically whether we're doing emission or we're doing absorption. Here's our definition for the absorption coefficient, fractional change in I per unit length. Usually in the case where this term is negligible, we're doing an absorption experiment. We make this I near 0 brighter than IB. We did the structureless line of width delta nu, we get this result. Now what I'm going to do is I'm going to introduce shape. So you can almost anticipate the result. It's going to be something like proportional to 1 over delta. Here's now the reality. This is my structureless line for transmission in K. This is a real line. Real lines have some shape. It might be kind of Gaussian or Lorentzian, but it's a shape. The transmission goes to 1 in the wing, so the line has finite width. What we do now is we imagine that we have to consider one segment of this actual line. We'll call this the frequency range d nu. Now K, therefore, has a shape that's inverse from, take the negative log. So there's some sort of a factor right here that's based upon this shape. So now I'm going to define a line shape function, which is basically nothing more than K over K integral of K. So I'm going to define a line shape function. I think it's defined on the next slide that mirrors the shape that we get from K, but it's defined in a way that the integrated area is 1. So basically, now this is the summation. We have some observed K, some observed transmission, which converts to some observed K. I look at this line and I see that it has some width FWHM stands for full width at half the maximum. Now I'm going to represent this shape with what's called the line shape function that represents this shape, but normalized so that this area is 1. So we define phi to be the instantaneous or local value of k, like right here, divided by the integral of k over the line. That way, the integral of phi is 1. Purely a shape factor. Purely a shape factor. And so if you think about how this relates back to what I did before with the line with delta nu, it's no surprise that my representation here is going to be something like 1 over delta nu. Anticipate there that what the term I had before is going to be replaced by this. So here we are. We're back to the Einstein theory. And if we had now represented this as a shape factor, instead of the Milne term, I now have a variable probability that depends upon frequency. So before we had a constant here. Now we have to recognize that it depends on frequency and width, d nu. So basically, I redo the Einstein coefficient so that this quantity now is the probability of undergoing spontaneous emission in this range. And then if I integrate over the entire frequency here, I'll get A. So basically, I'm just inserting a shape factor. Same for the B's. So when you do this, go through the algebra, redo the energy balance. You can find that the new value of K is exactly what we got before, but instead of 1 over delta nu, we have phi. So it's actually physically reasonable. So what does that say? The spectral absorption coefficient that governs the attenuation of light is nothing more than a constant times the number of absorbers in the quantum state that absorbs the light, the Einstein coefficient, which we have to find somewhere. This term here, which is often h nu over k, is a characteristic temperature, and which tends to be typically much larger than T. So this is called the induced emission term, usually close to 1 times the shape factor. So what does this tell me? This is why when you do quantitative absorption, you need the third element of line positions, line strengths, and line shapes. You have to know something about line shape in order to exploit this K and convert a measurement of the transmission to something you want, which is usually the number density in the absorbing state. Measure the attenuation of light. You know the path length L, because remember this is per unit length. So you measure the transmission, fractional transmission, take the negative log, divide by L, and you're back to K. And you have some constants. The thing you're after, the number density in that state, the Einstein coefficient, and phi. So now if you understand phi, you can solve for N1, if you also know B1, too. Remember, this is the number density in a state. So if you want the number density of the species, what do I need to do? Invoke the Boltzmann relationship. The Boltzmann relationship tells me what fraction of species are in level 1. You have to tell me the temperature. You have to tell me the energy of that state. So I'm going to go from my measurement of transmission and the knowledge of the length to the absorption, the measured absorption coefficient. If I know the constant, this is a constant, and if I know the line shape factor, and if I know the temperature, I can solve for my number density in 1, and because I know the temperature, I can solve for the total number density of the species. That's how you get to the measurement of the density of the species, measurement at a specific wavelength. If you're bothered by this thing, you can play a trick. You can integrate over the line, get rid of this term. Integrate over frequency of this line, this phi of nu integral goes to 1. That quantity, k nu dl, becomes what we call the line strength, the integrated absorption of line strength. So that number, which you would get by integrating the absorbance over the line, is now, removes the line shape function. It's now a function only of T, B, and N1. Again, I can go from N1 to the number of the species using the Boltzmann relationship. So what is this telling me? I can measure the species density from an absorption measurement if I know B. B is basically a variation of the line strength. So there's the strength of the line that's that we need to know. Where would we get that? We get that from tables, or we would calculate it. I'm going to show you some alternate ways of getting this. So to sum up, the spectral absorption coefficient, which we would use if we're doing a calculation of absorption or emission, nothing more than the line strength times the line shape function. That is specific frequency nu within a given line. Okay. So there's a lot of different ways that this line strength appears in books. It depends on the units, so you have to be really careful about this. If I want to write this as a function of, I can write it as a function of the B coefficient, but remember A's and B's are related, so I can also write it in terms of A. I like this method because the units are clear. The units of B are confusing. The units of A are seconds to the minus 1. So when I look at this expression, I know the wavelength, the units are going to be in centimeters, number density per unit per centimeter cubed per second, dimensionless. I immediately see what my units are of this line strength. So if I see the units of line strength are in these units, I know where I got this. Spectroscopists in the UV invisible often will use an alternate form. It's called the oscillator strength F. So instead of an A, they'll use an oscillator strength, and that was derived by the physicists who were wrestling with how do you characterize the oscillation from a dipole, an oscillating electron, a dipole. They introduced something called the oscillator strength that we'll talk about just briefly. So there's different ways of getting at S. They're all equivalent. It's a question of what database are you using? Are you using a database for A, or are you using a database for F? Different groups of people use different things. The oscillator strength is basically a ratio of the perceived strength of your oscillating dipole of your molecule versus what it would be for a classical free electron. That's what it means. So the oscillator strength is a measure of how strong is this process relative to what it would be for a freely moving electron. So therefore, the range of F's is 0 to like 1. So your notes will give you these, a lot of examples where the units are specified, because also you get into trouble when you look at the units for something like this. Alternate units that can be employed. So I tell you what it is in simple units of centimeters squared hertz. So there's ways to get to the oscillator strength that we care about. If you give me the oscillator strength, I can get it. But the strength of the line still always depends upon the number of absorbers. We frequently will invoke the ideal gas relationship that P equals NKT. Now they're saying that number density in level 1 can be represented as a partial pressure of 1. We use that to go back and forth because there are also groups of people, especially in the infrared, that use units of S that are centimeters to the minus 2 per atmosphere. Sounds weird. Common. So you have to be comfortable going back and forth between different expressions of line strength. They're all equivalent because there's only one fundamental A or B coefficient. Okay, so what do you want to keep in mind? You want to keep in mind that the spectral absorption coefficient K, which describes either emission or absorption of light at frequency nu per unit length, is nothing more than the line strength times phi. Why we care about phi eventually. Now, frequently, H nu over KT is much bigger than 1. That's the energy spacing right here. So especially if you're doing electronic state, where the energy differences are electron volts, you can neglect that induced emission term and find some simple relationships. So you can go back and forth, and I give examples in my book of how you can go back and forth between different systems of units. So here's an example. So if you're a wavelength of 1.44 microns, that's 1,440 nanometers, H nu over K is 10 to the 4th. So you can see right away, that's why frequently you can neglect the minus, this is the induced emission term. It's 1 minus this term. So this term is typically really small. So in this certain limiting case, you can find relationships between F and A. For example, here's one. Relationship between the oscillator strength and A is nothing more than a number times the ratio of the G's in wavelength in centimeters. Tau is 1 over A. So tau is the average lifetime for spontaneous emission. If A is 10 to the 6th per second, which is a typical number, the average lifetime is 1 microsecond. So everything boils down to A. If A is big, probability per second of emission is big, that means strong absorption. If A is small, weak absorption. For an electronic transition of, say, OH, it might be 10 to the 5th. Row vibrational transition of CO from 1 to 0, the number is like 30. The average lifetime is 30 milliseconds. So there's a huge difference in oscillator strength between row vibrational and row vibronic. Okay, so here's another terminology. Resonance transitions are ones which couple the ground state to the first excited state. So I'm talking about electronic transitions now. So if we talk about a sodium atom, and we have to characterize the transition we're looking at. Here's the transition. For atoms, and we'll learn more about this later, for atoms, we characterize the lower state and the upper state. And this notation tells the spectroscopist which electronic energy level we're talking about. For atoms, it's typical to write the lower state on the left and the upper on the right. For reasons I don't understand, the molecular people do it the other way around. You have to be careful about these things. This notation is called the term symbol notation. It tells me what I need to know about which electronic states are we talking about. Turns out that for sodium atoms, this ratio is about 1. And for a wavelength of 589 nanometers, which is isn't visible, kind of the orangey yellow. The lambda is orange centimeters. Now, the convention, so atoms is lower, upper, molecules is upper, lower. The molecule people often also write an arrow to tell you whether you're talking about absorption or emission. Now we can take this expression that we had on the previous slide and find this number here. So this is a number, F tau. So if the measured time is 16 nanoseconds, that means the A is 0.6 times 10 to the 8th. So where do we get A coefficients? Once we have them, we have an A coefficient or an oscillator strength. We have everything we need to know to convert our measured transmission to a number density measurement. Where do we get them? They're mostly measured. They're hardly ever calculated. There may be some theories, but they're usually referenced to some experiment. So this is telling you that if I could put a molecule in level 2, atom in level 2, and if there were no collisions, if I just watched the number in that level, decay on average in 16 nanoseconds. Measure that decay. That would therefore be, that'd be one way of determining A, and that's one way that it's done actually. Or I could measure the absorption under conditions of known absorbers. Some situation where I know the temperature, I know maybe it's pure sodium atoms, it's 1,000 degrees Kelvin. Measure the pressure, measure the path length, measure the attenuation, and solve for A, solve for F. So a measurement of absorption is a common way to determine the oscillator strength or the line strength. Much harder to do an absolute emission measurement. Much harder to do an absolute, because there's a lot of factors that go into an absolute emission measurement. Okay, so spectral absorption coefficient. Here's some examples now. These are sodium transitions. Sodium is in the left-hand, the first column of the periodic table. It's called the alkali metals. They're the simplest ones to deal with because there's only one electron that's not in a closed shell. Simplest case to deal with. Everything else harder. But this notation tells me something about this. Remember, this is lower and upper. I'm going from the n corresponds, the 3 corresponds to the so-called principal quantum number. The 2 corresponds to the 2s plus 1 for the spin. That means the spin's a half because there's 1 electron. This has meaning. But the oscillator strength is 0.33. Here's the oscillator strength for the other case. When you have a p electron, it can have either 1/2 or 3/2. The oscillator strength is twice as big. If I look at some other strange ones, the oscillator strength is small. So the oscillator strength is a measure of how much absorption or emission that you would see. Now, what if I go to some molecules? So notice that these oscillator strengths are pretty big. They're not 1, but they're significant. What if I go to something like a carbon monoxide, rho vibrational transition from 0 to 1? Rho vibrational. Band center is at 2,000 wave numbers, that's 4.6 microns. The oscillator strength is 10 to the minus 5. The oscillator strength is really small, meaning the probability of absorption is really small. The probability of emission is really small. I go to the first overtone. This is the fundamental. This is the first overtone. I go down by couple orders of magnitude. But the overtones they're not forbidden, but they're weak. Notice this, there's nothing in here about temperature. These are just probabilities. Nothing in here about temperature. Now if I go to OH, this is a rho vibrational transition, I get still 10 to the minus 6. But now if I do OH for an electronic transition, from the ground state, this is called the 2 pi 2 sigma transition. This is an UV at 300 nanometers, 10 to the minus 3. So you might think that that's a small number, but it's actually a pretty good number for a molecule. The biggest oscillator strength that I know about for a diatomic molecule is CN, for which the rate it's about 0.02, 50 times bigger than OH. So notice the huge difference between, say, OH and CN in their probability of emission or absorption. Very molecule specific. Okay, so we've covered a lot of ground here. The way to think about these radiative and non-radiative lifetimes is here. Imagine we have some molecules or atoms in upper level U, and they're able to radiate to some combination of lower levels. We could write an equation for the rate of change of population in level 2 due to the spontaneous emission only. So I'm only considering spontaneous emission. So we have to imagine that there's no collisions going on. I'm only going to consider this one effect. Rate of change would be the instantaneous value of n times probability per second of each of these things. So when we do emission, you have to talk about probabilities. So that says that if I have an initial value of n sub u 0, I park some number in level u and leave them alone, they'll decay in time by this simple exponential relationship. Or in other words, the average time is 1 over the sum of the a's. There's a sum here because there are multiple possible lower states you have to consider. So there's a simple relationship between radiative lifetime. It's called radiative lifetime. Sometimes it's called a zero pressure lifetime because only at zero pressure can I neglect collisional effects. In the absence of collisions, they will decay on average in a time that's 1 over the sum of the a's. If, however, there are other contributions to the decay, I'll go back and I could do the same thing, but now it's the rate this probability per second, and that may depend upon collisions as well as the radiative. So there's non-radiative decay and there's spontaneous radiative decay by itself. When you have the simultaneous probability, then the average lifetime, you have to do a parallel sum. So it's 1 over tau is 1 over the sum of the 1 over tau is for the radiative term and the non-radiative term. Okay, there's a lot of equations here. I'm not going to spend a lot of time on them. Just to show you that you have to be able to go back and forth between all sorts of different systems of units. Typically, they're all centimeters, but sometimes it's atmospheres. Always the number density of species in state 1 is here, but you may want to do it per atmosphere because it's done that way, centimeters minus 2 per atmosphere. So if you have when somebody gives you the line strength, you have to pay attention to the units. It might be centimeters to minus 2. It might be centimeters to minus 2 per atmosphere. There's different possibilities. Now, in the end, they all have to have the same A coefficient. They all have to have the same oscillator strength, but it's just units. High-tran, for example, uses units of centimeters to minus 1 per molecule per square centimeter. Looks pretty weird. But if you have to now integrate, and when you convert that to these units, you have to then multiply, you have to take into account P and N. This is per molecule, this is per atmosphere. That's the problem. How do you get there? You go back and forth with P equals NKT. If you want to find these units in terms of the high-tran units, you've got to invoke P equals NKT, and you have to remember that in that system, pressure units are dynes per square centimeter, and I got to go to the atmosphere, so I got to recognize there's 10 to the 6th dynes per square centimeter per atmosphere. It's just going back and forth. So you can relate the line strength, for example, in these units. High-tran value, multiplier and T. That's a common problem for us, is that my group likes to use centimeters to minus 2 per atmosphere, and high-tran uses different units. There's a lot of alternate forms for Beer's law. Beer's law is nothing more than the fractional attenuation of light. So this is the common way we write it, K nu L. If the spectrum are complicated and have overlapping features, we'll convert this to n sigma L. And now we call this the cross-section. Length is always there. But if you want to do it in terms of this K includes the number density. In this case, we separate out and it includes the number density in the absorbing state. In this case, we take the total number density of the species and represent what's called the cross-section. Sometimes, especially for big molecules, we'll do it this way. Again, they're all related. There's only one Einstein coefficient. But we have to be able to go back and forth. And I'm not going to go through this here. So you have oscillator strengths. We've got A coefficients, B coefficients. They're all related. I like the units where we talk about the probability. I like A myself because it's very clear what the units are. It's per second. Probability per second of emission. Now, what about temperature dependence? So people are asking about the line strength. If you know the line strength at any temperature, you can find it at any other temperature, but you have to be very careful about the units. So you can show that if we go back to if we represent the number density in level 1 to the total, I can invoke Boltzmann's relationship and use that to find the relationship of the line strength at temperature T at any relative to any initial temperature where I might know the answer. So I've got to form the ratio of the partition functions. I've got to form the ratio of T to the reference temperature, and I've got to keep in mind this exponential term. So you can do this. You can go from any line strength to any one temperature. You can go to another temperature, but you just have to be careful about the units. If it's these units, this is the relationship. If it's these units, it's this one here. All in making use of P equals NKT and the Boltzmann relationship. Why do I care about this? Not only because you need to know the line strength at the condition of your experiment, but this is the key to understanding how you can measure temperature by measuring the integrated absorption over any two lines. So if you do this, then that's the most sensitive way to determine temperature. Okay, sometimes in the infrared, people will talk about a band strength. Maybe we have carbon monoxide, P&R branch. You want to know the strength of a line, but maybe all you can find in the literature is the band strength. The band strength is nothing more than the sum of the line strengths. Now we have, in the case of a fundamental transition 0 to 1, we have to sum over all the possible values of J, and we have to recognize there's both R and there's P. And you can write it in terms of the number density in those states, and you can recognize that you have degeneracies, and you can do the algebra, and you can convince yourself that when you sum up all the R lines and all the P lines, write it in terms of A, recognizing the sum of the J's must be 1, you can come back to this. Basically, there's a way to go from band strengths to line strengths or from line strengths to band strengths. That's only done when we talk about rho vibrational. When we talk about rho vibronic transitions in the ultraviolet and the visible, we almost always work in terms of oscillator strengths. Anyway, so there's a lot of stuff here. Oh, this is an interesting one. Let's look at the band strength of CO. Actually, one of my students did this around 1982. And we found that the sum of all the line strengths for CO was about 280. The interesting thing is to now convert this to the Einstein A coefficient. And you get a number like 36. And what that means is that the average lifetime is 28 milliseconds. Yeah. If you put a molecule of carbon monoxide in level 1 and leave it alone, it emits on average in about 28 milliseconds. So the lifetime is pretty long. If I did this for OH, the lifetime would be a microsecond. These lifetimes are related to the A coefficient, inverse of the A coefficients, or related back to the oscillator strengths. So rho vibrational transitions are weaker, but very helpful. Okay, how did I do in time? I'm probably about right. So in 1 hour or 50 minutes, what we did is I introduced the equation of radiative transfer as the way for us, and the Einstein coefficients, as the way for us to quantify absorption of light. Why? Because we want to use absorption of light to measure things. It turns out that that same K is the one you would use if you wanted to do a calculation of emission. Calculate emission from a hot gas, it's the same K. If you want to do line-by-line calculation of the emission of light, you'd use the same Ks. And those come back to the number density of the molecules in the A coefficients. So if you know A, you know B, 1, 2. If you know A's, you know the B's. If you know A, you know the oscillator strength. You know everything. And those are probability per molecule. So now you have to have the number of molecules to get the ultimate output of emission or absorption. So it all is very compact. Everything boils down to the absorption coefficient and whether it's optically thin or optically thick. But we realize finally that you can't neglect the absorption, the line shape factor. So in the next hour, we'll talk about line shapes. At that point, we'll have dealt with line positions, line strengths, and line shapes. And we can put it all together, and we can do quantitative diagnostics. Find that it's only a half step past that to do fluorescence. So any questions? Well, we can expect you to, cover a lot of ground fast. It is interesting to find out these microscopic systems, probabilities, fundamental probabilities. Think of these processes: absorption, emission, and induced emission, spontaneous emission, and induced absorption. These are three fundamental processes. And we did this by neglecting particles, because the gas has to behave the same regardless of whether it's particles there or not. Frequently, you go to equilibrium to find a relationship. Then you go away from equilibrium where the fundamental quantities don't change. Like a reaction rate constant in chemistry. The reaction rate constant doesn't know whether the gas is in equilibrium or not. The only what you know, though, is that in equilibrium, reactions are balanced. So now you have a relationship between the forward and the reverse reactions that you found from equilibrium arguments, but the rate coefficients don't care whether you have equilibrium or not. It's a real common trick. Another common trick is you write a rate equation, and then you say, well, at equilibrium, certain terms are 0. Sometimes we call this a steady state approximation. Okay, so let's see, we're at 10:49. We can probably start again at 10 after, 5 after, 10 after, about 10 after 11.